Let's continue to the fifth subsection, piecewise interpolation by lower degree polynomials. Okay, here I need tell you the polynomial interpolation method has a disadvantage. Okay, in general, the interpolation is not convergent when the number of nodes, or we know the number of nodes is equal to the degree of the polynomials plus 1, right? Okay, that means when the number of nodes tends to infinity, but the error is not convergent to 0. Okay, here we need to review the remainder term. Okay, here in this theorem we have null. Okay, the remainder term or the error, right? The error fx minus pnx. Okay, we know if fx satisfies this condition, it is n plus 1's differentiable function in NB, and also we choose the nodes x0 to xn also inside the interval. Then we can obtain the error term. Okay, Rnx is equal to this form. Okay, f the n plus 1's order derivative of f at some c. The c also inside the interval, divided by n plus 1 fraction number multiply wn plus 1x. And we know wn plus x is this polynomial, n plus 1's degree polynomial, x minus x0 multiplied to x minus xn. Remember? Okay, and also here, what means the convergency? Convergency means, okay, if we add more and more nodes, that means we like consider when n goes to infinity. When n goes to the n here, n means n plus 1 is the number of nodes, right? So if we want convergency, that means when n goes to infinity, we like the limit of pnx is fx, right? It's okay. This means convergence. Okay. Unfortunately, here please note. Unfortunately, we don't have this convergency. Why? Because you also should know. Because here n here means the degree of the polynomial, right? And also here n means the number, because n plus 1 is the number of nodes. Okay, that means when you add one node, then you will increase the degree of Pn. Okay, however, high order or high degree polynomial is not good for computation. Okay, so here we don't have the convergency. Even you add more and more nodes, then the Pnx does not converge to fx. So this is a disadvantage for the polynomial interpolation method. We don't have convergency. It's okay for you? So you should know this fact. Okay, unfortunately, we don't have convergency. Okay, I show you an example. Okay, now if we consider the target function fx equal to 5 divided by 1 plus x squared, and we use equally spaced nodes in the interval from -5 to 5. Equally spaced node means, okay, when n here, I write here, please note here, -5, 0, -5. Okay, if n equal to 2, then that means we choose the 2 endpoint. If n here 2 points, okay, and if we choose 3 points, then we use this 3 points equally, right? Equally. And if we want to use five nodes, then we use equally spaced, uniform, and continue uniform, equally spaced. It's okay? It's okay means the points are uniformly distributed in the interval from -5 to 5. Okay, equally spaced node. Okay, that means, okay, by the formula, xk equal to -5 plus 10 over n multiply k. Okay, k from 0, 1 to n. It's okay? So, because the length is 10. 5 minus -5. So, the length is 10. 10 over n. Because we have, because n plus 1 nodes, then we have n segment. Okay, each segment, the length is, okay, is n, 10 over n, 10 over n, okay? So, xk equal to -5 plus 10 over n multiply k. Okay, now I show you the interpolation result by the Lagrange interpolation polynomial. Okay, degree m equal to 3 cases, 6, 8, and 10. Okay, so we show you the results respectively for the interpolation polynomials. Okay, this is a fugue, and I only show you the left side. Actually, it should be like this, because from -5. Okay, now you see -5. Actually, it should be like this. Okay, and 1. Okay, 2, 3, 4, 5. Okay, so this figure should be like this. Actually, it is symmetry. So I only show you the left side. It's okay. This is a target function fx equal to 5 over 1 plus x squared. Okay, and if we consider the case when n equal to 6, then you will obtain this figure of the polynomial like this. Okay, now you see, of course, this figure is not the because I don't draw this curve by program. Okay, so this just show you the property, not the very exact curve. Okay, so now you see, in the neighborhood of the orange point. Okay, now the arrow is small, but to the end point. Okay, now you see the arrow is big. The arrow is big. This is P6, and also this should be symmetry. So for the right side, like this, like a symmetry curve. Okay, like this. Sorry. Just like the symmetry case. So okay, maybe like this. Okay, symmetry. And if we consider P8, then the blue line is P8. Okay, then you see. Okay, so near the orange point, the arrow is also small, but at the near the end point, okay, now you see the arrow is increased. Okay, now okay, you see for the P10, now you see the arrow amplified near the two endpoints. Actually, this is a symmetric curve. So I show you like this. Oh, it should be more big. Okay. Okay. Just like this. Okay. Of course, it is like this. Okay. It's a symmetry case. Okay. So that means we don't have convergence. This is a very also famous counter example. It means the longest phenomena. for the high degree polynomial interpolation. Okay, so this result show us, okay, we cannot use high degree polynomial interpolation because we don't have convergency. Okay, so that means it's better to just use low degree polynomial interpolation. So in applications, we just use usually cubic degree 4 and 5. Okay, so it's enough. Not use high degree polynomial interpolation. Okay, and also we need to use because we cannot use a high degree, but in the beginning we know the degree equal to the number of nodes minus 1. So that means we cannot increase the degree, so we have to consider or use the piecewise interpolation technique. Okay, so what is mean? Actually, just come back to the figure. Okay, I clean the screen. Actually, if we just use, I show you, for example, this is a target line. This is fx, y equal to fx, and we take some sample points from the curve, right? Okay, now if we consider just use piecewise straight line or polygon line, connect each 2 points. Now you see, this polygon line is close to the curve, right? Of course, here we have big error, and now in order to decrease the error, then we add a node here. We add a point here, then we can use, now you see, another polygon line more closer to the curve. It's okay? And also here, we have a big error. Then if we add one point here, then we can use this straight line, polygon line, then more closer to the curve. Now we have convergency. It's okay for you? When we increase the number of nodes or the number of sample points, then we have the convergence. The polygon line converges to the curve. It's okay? So that means we just use piecewise method. Okay? So here, piecewise interpolation techniques. That means we use low degree polynomial interpolation, but we use piecewise. Of course, the difference between the lower degree piecewise interpolation method to the general interpolation polynomial. What's the difference? The difference is smoothness. Now you see, now we use polygon line, right? We use polygon line. Now we see the polygon line is not smooth. Here is not smooth. It's just C0. Okay, it's just a continuous piecewise. It is not a smooth curve. So this means we sacrifice the smoothness, but we obtain the convergency. It's okay for you? So you should understand, because the reason here, by the longest phenomena, we cannot use a high degree to decrease the error. Right now you see, you increase the degree, also the error is increased. So in order to decrease the error, we need to add more data points, but we cannot use a high degree polynomial, so we have to use piecewise low degree polynomials, right? Of course, the sacrifice is we cannot obtain smooth function. Okay, we sacrifice the smoothness. but we obtain the convergence. Okay. Now we just consider if by piecewise linear Lagrange interpolation, that means polygon line. Okay. So here now you see we consider the interpolation nodes x0, x1 to xn. Okay, and also inside the interval from a to b, right? And now we use just linear Lagrange interpolation in each subinterval xk to xk plus 1. Okay, then now you see, for xk we know the function value is yk. For xk plus 1 the function value is yk plus 1. Then we just use linear Lagrange interpolation on the two corresponding to the two nodes, then it is easy. Okay, for yk the node is xk, so the linear Lagrange interpolation basis is x minus xk plus 1 minus xk minus xk plus 1, right? And for yk plus 1, its Lagrange interpolation polynomial is x minus xk divided by xk plus 1 minus xk. Now you see, we just use a straight line. Okay, so that means here we are given data point here like this. So this is x1, x2, okay, x3, x4, x5, x6, for example. Now for each 2 points, we just connect by the linear straight line. Okay? Now you see we obtain a polygon line. It's okay? So this is just okay. You don't need remember this formula. You just need to understand the idea. Okay? So that means we just use piecewise linear interpolation. That means, okay, start from x0 to x1 we have 2 points, right? Then this straight line denoted by LH0 x. Okay, and the next x2 we have y2 here. Then we connect the 2 points by straight linear function. Then this linear function denoted by LH1 x. And the next x3, for example, here. Then this straight line denoted by LH2 x. It's okay. For each interval, we use a straight line linear polynomial to interpolate the 2 points. Okay, so we just use this symbol, but you only need to consider understand the idea. Okay, so the graph of the function y equal to LH is a polygonal line connecting these points x0, y0, x1, y1. So this point is x0, y0, right? This is y1, this is y2, this is y3. Okay, so it is called polygonal approximation. Okay, so if also we consider the target function fx equal to 5 over 1 plus x squared, then now if we use the piecewise linear interpolation method, then now you see connect the data points. Now you see we obtain a very good approximation polygon line to approximate the curve fx y equal to fx. Of course here we have angle, so it is not the smooth function. So we sacrifice the smoothness, but we can obtain the convergence. It's okay. So this is the idea by piecewise. Of course here we use piecewise linear interpolation. If you like, you can use piecewise quadratic interpolation. It means here I also show you the idea. Okay, now for example, we are given now 1, 2, 3, 4, 5 5 points. Okay, now if we use piecewise quadratic interpolation, that means we use 3 points x0, y0, x1, y1, and x2, y2 to construct a parabolic curve, right? Parabolic curve, because quadratic polynomial, right? And from by the 3 points, we can draw another parabolic curve. It's okay for you? So this is piecewise quadratic polynomial. Of course, here, because x2, this point x2, y2, the function value is y2, right? At this point, okay, only c0. Okay, if we change the data points, you will see the for example here, this point here, like this. Now, by these 3 points, we can obtain the parabolic curve like this. Okay, so it's not good. It's not easy to draw by hand on the screen. Okay. Okay, here you see for the 3 points, we obtain a quadratic polynomial parabolic curve, and also by these 3 points, we also obtain. Oh, it's not beautiful, right? It's not. Oh, sorry. I choose draw the curve firstly, then we choose the point. Okay, we choose the point here. Okay, for example, this is a parabolic curve. Okay, now you see, at this point, it is only c0. It's not a smooth function, right? If you choose use a smooth function, then that means 1, 2, 3, 4, 5. For 5 points, we should use quartic degree 4. Then you will obtain a smooth polynomial. But you need to use degree 4 interpolation. Now we just use degree 2. We don't increase the degree. Then you add points, more points. You don't increase the degree for each segment of polynomial. It's okay for you? So this is piecewise lower degree interpolation. Then, by the interpolation Riemann term, Riemann theorem, if f(x) is a second differentiable in AB, now we just consider in the example we use piecewise linear interpolation. Then we can obtain the error for each segment. Fx minus LH kx. Then it is just this error term, right? Second derivative of fc over 2 multiply x minus xk multiply x minus xk plus 1. It's okay? Just use the Riemann term for linear interpolation. Then here the error for each segment, right? We have this error. Then the maximum of the error is the bound. Okay, we can define M2 is the maximum of the absolute value for the second derivative of f at the interval. This is a constant M2. Okay, and multiply the absolute value of x minus xk and x minus xk plus 1. Okay, then by this formula we can compute its maximum value, because it is just a quadratic polynomial. Okay, so it is easy to obtain its maximum. Actually, here, okay, if we consider the step size hk by k plus 1 minus xk, then h is the maximum of hk, then for each term less than h, so here h square. It's okay. And then when we increase the number of nodes, okay, because when n goes to infinity, that means the step size h goes to 0. It's okay. xk plus 1, this is hk, the step size. right? And H is the maximum step size. So if we add more and more nodes, then that means the H goes to 0. Now you see, the arrow term goes to 0. So we have the limit, right? So when H goes to 0, the limit of the piecewise LH means the piecewise linear interpolation polynomial. Then the limit is fx. Okay, so here you see the figure. You see the figure? Now you see? More closer to the curve, right? Convergence. It means we have the convergence. Okay, so at last, note that for piecewise polynomial interpolation, the degree of the polynomial is not changed. This is the key, okay? We don't increase the degree of the polynomial when the number of nodes is increasing. So that is why we can have the convergence. Okay, actually, it is very popular in practice to use piecewise lower degree interpolation method. Okay, so that is why I want to introduce to you to let you know, okay, if in your research, okay, you cannot, you need a degree, you need a deal with or interpolate many data points, okay, then it is not good to use high degree interpolation, but to use, okay, lower degree, piecewise low degree interpolation. It's okay?